During the last talk, we talked something about the hierarchy of constraints. Now, within any given theory, one tends to think of the constraints as being boundary conditions, such things as boundary conditions and the theory itself, the equations of motion which form that theory. But there are some overarching constraints over and above that that one often doesn't think about. And those overarching constraints include such things as space and time itself, if one's dealing with a vector differential set of equations. But they also contain things such as conservation laws or symmetries, conservation laws such as the conservation of energy or angular momentum spin of momentum itself. These are underlying constraints which can be expressed perhaps as equations, which also constrain any possible solutions that one might have to any theory. So, and space and time themselves, even the things one's using to describe a theory, may themselves be subject to a deeper level of constraint or variation. So space and time within relativity, for example, change depending on your point of view. So these other constraints are extremely important for any theory. Now, what I'm going to do is in this presentation, I'm going to talk about setting up a quantum mechanics. I'm not saying setting up quantum mechanics because there isn't only one quantum mechanics. There are several, relativistic, different ways of looking at the same quantum mechanics, wave equations, for example, or looking at commutators and having a look at the developments of Poisson brackets, commutators, the development of those, and setting up from different starting points. And it's the starting points, it's the foundation which I want to talk about here. So without further ado, let's get into that and start talking about such things. And as an example, I want to talk, which most of you are familiar with, but I want to just run through how to build a non-relativistic wave mechanics. This is Schrödinger theory. So what goes into the equation? What is the basis of the equation, apart from space and time, which we've already talked about, because the derivatives we're going to talk about are spatial and temporal derivatives. But what's sitting underneath that theory? What else does one need to put in, apart from the constraints of space, time, and energy, the 5 basis things? Well, up on your screen at the moment is a very quick derivative of Schrödinger non-relativistic wave mechanics. I normally take about an hour to do this in final year level at university to explain this stuff. I'm going to do it in about 5 minutes. So it's maybe something we can come back to. But the basic things that are going into Schrödinger quantum mechanics are 2 quantum things. Now you can take these things as coming from experiment. Energy is given by Planck's constant times the frequency. E is h bar omega, is one of those 2 things. And the momentum, vector momentum, is given by Planck's constant times the wave number, vector wave number. Now these things are derived from experiment, but also from relativity. The second of these relations, the Dubrow relation, is called the Dubrow relation because Dubrow derived it theoretically about 7 years before it was actually measured experimentally. So one of those rare things which comes first from theory and then was later seen in experiment. And the way that Dubrow derived this is beautiful. And if you want to look at some of the most beautiful physics and the most beautiful French at the same time, just read Dubrow's thesis in the original French. It's gorgeous. But there he shows how you derive quantum mechanics, an element of quantum mechanics, from relativity. That's a bit fashionable these days to say it's pretty amazing that relativity and quantum mechanics just so happen to sit on top of one another, but it's not amazing at all. That's how the thing was designed in the first place. These are the underlying relationships that you start with as the basis that you're going to derive a differential equation from to describe the wave nature of matter. So what is the wave nature of matter? Well, the wave nature of matter is put into the theory as a complex wave function. Now, by complex here, I don't mean it's complicated. I mean that it has the imaginary number, the square root of -1i. So a Schrödinger wave function could be described in terms of space x, y, z as psi of r and t. It's a 4-dimensional, 4-component wave function. Be written as a complex exponential as some normalization factor that says, for example, that you just have one electron that normalizes to a single particle times the exponential of I k dot r minus omega t. It's a 4-dimensional, single-valued wave function. And what happens with that wave function if you vary in either space or time, the thing waves. The rate of variation in time is related to the energy through E is h bar omega. So if you just fix space and let time run, then it runs according to omega t. If you, on the other hand, just look at the variation in space, so you take a fixed time and let space vary, then it will wave according to the relationship P is h bar k. So that's what you're doing. Now, remember what I said in the last lecture, that mathematics can enlighten, but it can also obscure. You have to realize that what one's doing in setting this theory up is not only taking on board space and time and E is h bar omega and P is h bar k, but it is also taking on board the mathematics which describes this. And that mathematics is complex in both senses of the word here. And here is complex mathematics being put in. And one's then sitting inside a framework where one's talking about a single phase value wave function. Now this sounds reasonable, sounds great, but it's a bit dangerous if you know by reading Dubrow's thesis how P is h bar k was derived in the first place, because P is h bar k was derived because there are two phases involved. And those two phases are such that they are everywhere in all space and for all time in phase with one another, but that they behave differently under a Lorentz transformation. One of the two waves varies according to the Lorentz law of scaling of clocks, slows down, and the other one varies according to the relativistic law of increase of energy with frequency, E is h bar omega. So Dubrow found a way of looking at things both increasing in frequency and decreasing in frequency in such a way that they remained everywhere and for all time in phase. And that's quite a complex concept, but it means that if one's taking a single valued wave function like this, one's missing something out from at least the theoretical derivation of P as h bar k. Now, you don't need to worry about that necessarily, because now that's an experimental fact as well. But in fact, it does say something about the mathematical framework that one's looking at here, and one's introducing the mathematical framework. Now, having implicitly introduced that mathematics, and this is not the mathematics, it's a mathematics. Complex mathematics is not the only mathematics. Then one could derive within that mathematics differential operators extracting energy and momentum for the assumed wave. And these operators are well known. I've just written them down here. The operator for energy is IH bar d by dt. For momentum is minus IH bar grad, or nabla. And that allows one to write the operator, to replace energies with the operator for energy and momentum with the operator for momentum for this mathematical framework. Now, momentum is not the operator for momentum. This is just a mathematical description of what's happening with a quantum wave. And one must not confuse the maths with the physics. But having produced the maths, one can introduce an operator equation which parallels the classical Hamiltonian. What's a Hamiltonian? Hamiltonian is that expression that gives the energy and in classical physics, kinetic energy is given by half mv squared, which is p squared over 2m. And there might be a potential energy in there given by potential v. So the classical Hamiltonian operator for this mathematical framework is h bar is p hat squared over 2m plus v. V is a three-dimensional potential in x, y, and z. Now, if you do that, you can write down the Schrodinger wave equation. That's what Schrodinger with some friends did. Of basically h hat psi equals e hat psi, which is at the bottom of this slide. There you have it. You now have a quantum mechanics. And it's a bit of work, really many people's career of works to use that in designing and thinking through things that lead to quantum devices. But that's really what quite a lot of physics has been over the last century or so, is developing and moving forwards within the thinking picture of non-relativistic quantum mechanics. So that's one quantum mechanics very, very quickly. And if you want to know more about that, then perhaps I'll do a later lecture of this, derive the thing really from first principles and show what sits in there. But that is an hour-long lecture, or at least it was to my students in the past. So let's go on and have a look at some other quantum mechanics. And I'm going to talk about how to build a quantum mechanics, and develop complexity from simplicity. Now, I'm using as a basis space-time root energy only, but there are going to be other things coming into this. This is not going to be the only set of constraints in there. The constraints are going to be an energy-like constraint, a Hamiltonian-like constraint, that sit overarching over and above this. I want to try and say what else you put in, and I'm going to make a comparison between now not quantum mechanics, not non-relativistic quantum mechanics, but Dirac quantum mechanics, relativistic quantum mechanics. That equation's up in the top right, very briefly written in a modern form. That's I d slash minus m acting on some wave function psi is equal to 0 is the Dirac equation expressed succinctly. What are all of these things that are in this equation, in the Dirac equation? I is again the square root of minus 1. So one's sitting in a space which is a complex space. What's that thing d slash? Well, d slash here is a derivative, d by dx, dy, d by dy, d by dz, d by dt, a vector derivative, but it's a vector, that's the d. The slash part of this says that with every element of that d is associated a Dirac matrix, a Dirac gamma matrix, in fact, in this case. Either gamma 0, gamma 1, gamma 2, gamma 3, or 1, 2, 3, 4, depending on how you want to label these things, with 0 being time derivative, or 4, and 1, 2, 3 being x, y, z in space, for example, or r, theta, phi in space. But look at this equation, look what's in it. What's in it is that vector operator, that hypercomplex vector operator, because it contains Dirac matrices, multiplied by the square root of minus 1, and then a mass. Look at the mass. That mass is different in that it's not got any of this complexity, any of this slashiness, and it doesn't have a square root of minus 1 in front of it. It's just like a lump of mass. And that thing operating on some kind of object, it turns out to be a spinor object that this thing is acting on, psi, is equal to 0, is what the equation is written as. But that equation is not just the equation. It sits embedded within a mathematics that includes the Dirac algebra, that includes the complex algebra, and that includes this idea, whatever it is, of mass. When one's looking at an equation like this, one really needs to look at all the elements of the equation and in what context that equation sits. So really we should be looking at the I, the d slash, the m, psi, what 0 means in this context anyway, and what's that equals thing anyway. So to really understand what's happening in relativistic quantum mechanics, and if you do want to understand that, then I recommend that there is only one recommended text for this from me, and that's Dirac's own monograph. There are lots of relativistic quantum mechanics texts, but as far as I know, and I would stand corrected in this, the only one that really exposes all of the internal difficulties and struggles that Dirac had in developing this quantum mechanics is Dirac's own. Many other textbooks miss out the hard bits. Dirac will look at the bits that he doesn't understand and go, wow, I don't understand this bit. How does this work? I don't know, so we'll drop it and do something simpler because I don't know how to handle it, frankly. Dirac will say that explicitly. Even in the 4th edition of his textbook, where he thought about this for decades, he will say that explicitly. Other people just go straight to the equation that Dirac gets after he's thrown out some of the bits that he knows he's not able to handle. But that's the Dirac equation, very briefly, and it's a lot of work to understand Dirac theory from Dirac, which is so. So that'll take a couple of years if anybody doesn't know it already, but all of you do, so that's fine. What I want to talk about, though, in this talk is designing another quantum mechanics. Now, that quantum mechanics is expressed by the equation below, d mu psi g is equal to 0. It's a similar form to the Dirac equation in that d mu is pretty much identical. It's isomorphic to the d slash operator in that Dirac equation. D slash and d mu have the same content, but there's no I. I is missing. This scalar square root of minus 1 is missing. And that psi there isn't the same as the psi. The psi in Dirac turns out to be quite a complex thing. Turns out to be electron and positron spin up and spin down, a 4-component spinner, which can be expressed in different bases. Now, as I say, if you really want to understand this, go to Dirac directly. And that equals 0. This is a standing joke in physics, that you can express the entire universe as d universe equals 0. All you need to know is the full wave function of the universe, and this psi g is a wave, eventually is going to be a wave function like the one we introduced in non-relativistic quantum mechanics. That d mu is a 4-dimensional vector operator, d by dx, d by dy, d by dz, d by dt. But then that vector operator contains built into it the mechanics of special relativity. It has built in, it's defined below, d mu is d by the alpha mu dx mu. So you've got your d by dx, your partial d by dx mu, but you've also got a 1 over an alpha mu. And what's that alpha mu? That alpha mu is a 4-component vector, time, space, 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 where those alphas are unit vectors in time, that's alpha 0, and unit vectors in a 3-dimensional space. 3-dimensional space, x, y, z, r, theta, phi, whatever coordinate system you want to use, doesn't matter. Will matter for solutions, doesn't matter for the base equations, provided that it's a conformal orthonormal system. So anything that has a 3-dimensional, a 3-way coordinate system that reduces to something that looks like a box, a 3-dimensional box, as you take it infinitesimal, will work here. So any well-behaved coordinate system is going to work for this equation. It's a vector differential operator like d slash, and it's isomorphic to d slash. Those alphas are exactly isomorphic to the gamma 1, gamma 2, gamma 3, and gamma 0 in Dirac, or at least in one projection of Dirac, in the gamma matrix projection. So that differential, though, is a Dirac-Clifford four-vector derivative. Now, what do I mean by Dirac-Clifford? I mean that it's a Clifford algebra in those alphas square to either plus or minus 1, square to unity. That's a Clifford algebra. If they square to 0, we'll be talking about a Grassmann algebra. So this has aspects of a Clifford algebra. But it's also a Dirac algebra. Actually, it's a reduced Dirac algebra because the square root of minus 1 is missing, because it follows the Dirac commutation relations. So it obeys the Dirac. So this is sometimes called a Dirac-Clifford algebra, although actually it's simpler than Dirac, and it's a specific Clifford algebra. It's the Clifford algebra technically is CL13, and all that means, it has one element, in this case time, that squares to plus 1, and 3 elements that square to minus 1. So it's similar to the Dirac algebra, but it differs in that it doesn't have the square root of minus 1. We'll see what that does in a little while. So I'm now going to define a multivector. Now that multivector is going to be something which allows space-time to express itself in different forms. Now there's a thing called the algebra of forms which makes these forms explicit. What do I mean by allowing space and time to express themselves in different forms? Well, a simple example of this is you can have space, x, y, z, and time, t. There are 4 components in the base of this algebra. So it's, in some senses, a 4-dimensional algebra that one's trying to set up here, 4 dimensions, x, y, z, t. But there are objects that one can describe. If one defines either multiplication or division in this algebra, and in an algebra you usually want to have things like multiplication, division, subtraction, addition defined. So if one does that, one gets new kind of objects which are not either x, which are not x, y, z, and t. An example of this is simply x times y. One spatial dimension times one perpendicular to it, that's an area. So in terms, that would be in square meters rather than in meters. It's a completely different thing to x or y. No amount of xness is going to get you one of these, or yness. You have to have x times y to get one of these objects. It's a plane as opposed to a line. It's a bivector as opposed to a vector. Bivector It's defined by two vectors, something that's defined by two vectors. And in a four-dimensional base algebra, there are 6 of these because there are 6 ways of multiplying 4 objects in pairs. So you can have xy, yz, zx, but you can also have xt, yt, and zt. So there are 6 of these planar objects. So we're now up to 10 basic things: xyzt, xty, ytz, ztx, xtt, ytt, ztt, if you want to make everything rhyme a little bit. And so with a definition of multiplication, which remember, or in fact, division is more fundamental in this, and we're going to be using division more than multiplication. With a definition of division, what it means to divide one of these objects by another one of these objects, then one has this set of things. Now, why do I say divide instead of multiply? Because an area is a simple thing. X times y is clearly plane, measured in square meters. It's how big your carpet is. If your room's 4 by 3, then you've got 12 square meters of carpet to cover it. Why am I saying division? Because the fundamental things that we want to talk about are really more like divisions than multiplications between these objects. Now, what do I mean by that? Well, let me give you an example. What does it mean, really? Let's just do this. What does it mean to divide? Imagine you have I know some of you can't see this, but imagine you have a ruler and a clock. So, and we want to divide space by time. What does it mean to divide space by time? Okay, dividing space by space, x by x, you've got a 6 meter length, divide it by 1 meter, you get the number 6, that's fine. But what does it mean to divide space, a unit space by a unit time? What does that mean? We're talking about a physical thing that you're describing biomathematics, and you're going to use that thing we call division to define a new quantity, which is a space-time area. It's a space divided by a time. What sort of thing is that when it's at home? Well, dx by dt, I think most people will recognize that as a velocity, meters per second, dividing space by time. It's a different kind of object. Now, properly, in elementary, at school, and actually at university as well, in undergraduate university, one tends to be taught that velocity is a vector. It's given as one of the things that's an example of a vector. But actually, it's a bit more complicated than just a common or garden vector. A vector is something like the base element. It's actually really, it's really a bivector. It's really one kind of vector divided by another sort of vector. So velocities really never were vectors, you know. And despite the fact you have dx by dt, dy by dt, and dz by dt, these are the components of velocity, notice there are not 4 of them. There are only 3. And this means that this is a 3-dimensional bivector space of velocity. Now you also have dx by dy, and so on. You have divisions of space by time as well. And those are different sorts of objects. They're also bivectors, but they're not velocity. They are a different kind of bivector. We'll come on to that shortly. They all turn out within what we're doing here to be related. An example of things in this direction, this bivector direction, is actually going to be the electromagnetic field. That's going to be velocity is another example of what these things might be. But one's developing an algebra which has how many components we've got so far? We've got x, y, z, t, and we've got dx by dy, dx by dt, dy by dt, z by t. We've got 6 of these things. So we're up to 10 different kinds of objects, and they're in the second line of this equation just here. We have a scalar object here. We have a scalar object here. We have a vector object here, 4 components, t, x, y, z. These xi's, these small letter xi's, are just magnitudes. They're scalar numbers multiplied by a unit vector in time by a unit vector in space. That's a 4-vector, this thing just here, quantity. But from that, one could derive other quantities that are 6-component bivectors. That's alpha 0, 1. That's an xt plane, a yt plane, a zt plane. And this thing is a yz plane, which one assigns to the x direction. And this is a z x plane, which one assigns to the y direction. See why in later talks. And here's an xy plane, which one assigns to the z direction. And each of these can take a magnitude as well, in principle, in a very general theory. But of course, one hasn't exhausted all the possibilities with just lines and planes in a four-dimensional system, because one can also have volumes. So one of these volumes, x times y times z in meter cubed, is pretty straightforward. It's this one down here, psi 1, 2, 3 times alpha 1, 2, 3. Alpha 1, 2, 3 is a unit spatial volume. And an object can exist in this kind of form within this algebra that we're just making up. Theories are things one makes up. They're speculations, and this is a speculation. It is a theory. It is a quantum mechanics. Whether it is the quantum mechanics and whether it's to do it more useful quantum mechanics than, say, relativistic quantum mechanics of Dirac remains to be seen. It is a quantum mechanics. It is a, or it will prove to be a quantum mechanics. I'll show you why shortly, or in a later lecture. But these objects here, there are 4 of those that have 3 indices. So we're up to 4 plus 10 plus 6, 10 plus 4, 14. But there are also another couple of objects. There's a scalar. If we just multiply something in the x direction by something in the x direction, in a vector algebra, which this is a vector algebra, these things contract down to something which has 0 components. It's the scalar in this algebra, in this Clifford algebra. Now, in the Clifford algebra per se, that would be the number 1. Alpha p would just be the number 1. Now, I've distinguished it here by calling it something different because it's going to prove to represent something different. It's going to prove to represent a mass, something that transforms like a rest mass, a kind of rest mass. Again, that's for the future, but we'll see how that pans out. And there's another thing out here which is like a four-dimensional volume, x times y times z times t, and that could, in principle, have a value as well. Although for the things we're going to talk about some of the simpler things that are just don't have all 16 elements. This is a 16 linearly independent element thing now. So this now has evolved the complexity of a 16-dimensional, in a sense, algebra from the 4 dimensions of space and time, because one has defined, well, either division or multiplication, or even both. One gets a 16-component thing. And in fact, it turns out that for the physics we want to describe, we'll find that multiplication and division give the same object up to a psi. So it might be that, come to that later. But this is the algebra which we want to use based on space, time, and root. So I've said this is based on space, time, and root energy only. What do I mean by that? Well, these are objects here, these alpha 2, 3s, alpha 1, 2, 3. These are all derivatives. Well, not derivatives in the derived sense, but in the sense that one has gotten from multiplication of x times y times z. It's a spatial volume. So that thing has a form. Here is a form which is a line, a plane, a volume, a four-dimensional volume, a hypervolume, and a scalar, no volume at all. No. This is an interesting thing. It's like a point. P could mean point, but it's a point as opposed to a line or a plane. It's not a point in the sense of something that's so small that it's almost not there at all. It's as close as you like. It's not there at all. This is something which can have magnitude. A mass, a rest mass in a quantum particle can have magnitude. Mass of the electron, for example. So we want to keep that thing in there as something which can have a size, even despite the fact that it doesn't have a form of a line or a plane. So this is a point as opposed to a line, rather than a point as something which is almost not there at all. So we've got 16 space-time forms: lines, planes, volumes, hypervolume, and a Lorentz invariant scalar point. Now, I say Lorentz invariant, that's not because I'm putting in that it's Lorentz invariant. If I set a metric up here, which I've actually done implicitly here in the differential, that's a relativistic metric, then lines in this thing transform like 4 vectors, because mathematics is a relativistic algebra that's defined to work like that. This derivative here, the derivative d by d alpha mu dx mu, is a powerfully Lorentz expressive derivative. there's a rule which one can use to extend the normal thing that one does with relativity. I call it absolute relativity, where no quantity is allowed to appear at all in the mathematics describing the physics, because the physics always has to be a real thing. It has to be something that really is a line, that isn't some abstract thing, but that is a line or represents a line in real space that has some reality. And in order to make sure that happens at all levels, I'm going to make up a rule where I don't allow any quantity, I don't allow x to appear without having a unit x direction vector, without having the vector quantity of that x expressed in the mathematics. I'm forcing the mathematics to follow the physics, not the other way around. Now, this is not then a theory which I've just made up. It is that theory that follows from taking those axioms, from taking the axiom that one has space, time, and root energy only. So where's the root energy in this? Well, it's in the size of these quantities, and the size of these small letter chi's. That's your root energy. It could be zero. There could be nothing in that component. So, but as soon as those components get some value, then there is some amount of root energy that goes into them. Now, that root energy is not going to stay in them, because we're developing dynamical theory, and the differential is going to shift them to somewhere else. This is root energy moving around between unitary objects. And it's a dynamical theory of that sort of thing, like the Dirac equation or the Schrödinger equation, or even Newton's laws. So it's one of those that we're going to make up here. So I've said here d mu psi g equals 0 as being this general equation. And coming back to that, what does this mean? Well, what does it mean now? What it means is the 4 differential of a general multivector is equal to 0. Now, is that the theory? I've said it's the theory in its simplest form here, because it's not the whole theory that is going to be developed in this set of lectures. It is that expression which says that for a solution psi g, which is self-perpetuating, which remains the same, if one looks at a time or a spatial step of that, so one steps unit time, unit space, one makes a unit step, which is a quarter turn in phase, a 90-degree turn in phase, such that something traveling in the x direction transforms entirely, something traveling in the y direction or the t direction or the z direction, entirely transformed as a quarter turn, because x to y is a quarter turn, a 90-degree turn, so that you start with x and you have no x left and only y. This is a transformation equation. And what that equation is saying is it's saying that if one has a stable situation, it can only be stable if when it transforms, it remains the same. In other words, there's no change in the result. It doesn't mean that the elements are not changing. It means that for every element that changes to another element, there is some other element somewhere that changes to the element we first thought of, takes its place, that balances what's happening. That equals there doesn't mean is the same as. It means the result of doing such an operation is that there is no change. It doesn't mean there's nothing there. It means the change in the thing is the net result of that operation is no change. It's a differential operator here, which I've defined below. Now, there are different ways to write this kind of equation. I could write it as c mu, change in mu of psi g, is not equal to 0. But as I could write this as a transformation equation, or T mu, I've written it down here at the bottom. Transformation equation T mu on psi g is equal to some other psi star g, is equal to some other psi. That would be a transformation equation. You start with something, it changes to something else. Now, that is the same thing as d mu psi g equals 0 if the thing that it changes to is itself. So one could write this as a transformation equation, a different sort of equation, not a differential equation. I'm writing something like a covariant derivative here, for example, or we could write a rotation equation, where you say, okay, we have some object which is fixed and you rotate it, but it's still the same object, but then rotate it. Now, these things are not mutually exclusive. One can have something which is both evolving between different forms, like a differential, and is rotating at the same time. So you can have something which is internally translating, internally changing from one form to another, but the whole thing is at the same time spinning. One's then dealing also with a kind of covariant derivative with a connection. So also, this thing doesn't have to equal 0 on the right-hand side, just as there are a whole family of equations, the Laplace equation, for example, del squared psi equals 0, gives rise to a set of equations where on the right-hand side, you could, for example, put del squared psi is equal to d psi by dt squared, d2 psi by dt squared. One has the wave equation. You could put it equal to a constant. One has the Helmholtz equation. There are a whole set of these things which also may be expressed in the physics. This is only for an equation for a single, d mu psi g equals 0 is an equation for a self-sustaining system. So it could be a single elementary particle which is stable, or it could be one universe which is unchanging, which is where the total change in that universe is balanced, that something that has to conserve everything, spin, energy, and so forth. We could express that. So it's expressing the change of a quantum system, and this is it's a theory. It's a speculation. It's something that has been made up, and I've talked about this in several papers. The latest one is up in the top left, Journal of Physics Conference Series last year, June last year. So that's new quantum mechanics. Now, let's just have a look at what we're talking about. And I've talked about this here, but this is putting things up. I'll leave it up for a little while so that it appears in the video. But here's that set of constraints that I talked about just now in terms of what these different things are. I just want to go through them again anyway. So what have we got? We've got 16 components, and I'm going to give them names. And I'm going to say what sorts of things they are. They're space-time points, lines, planes, volumes, and a hypervolume. So alpha p, p here means point or pivot, eventually, is a Lorentz invariant scalar point. Why is it that? Because it turns out that, for example, a 4-vector squared gives one of these things, and if one then looks at the transformations with the Lorentz transformation, which is if you want to look at what these Clifford algebras can do, then there's a book, Gull and Lazenby's Cambridge group have published a lot of stuff online that you can look at for how this stuff works. There's a very good book by Lunesto about such objects. You can do a transformation on this and have a look at the physics of that transformation, at the mathematics of that transformation. And what you find is that these points, this p thing, is Lorentz invariant. Under Lorentz transformation, it doesn't change, so it represents such things as the rest mass, or as an invariant interval, the relativistic distance between two events. That's the sort of thing that it represents. It turns out that if one's developing a theory, an electromagnetic theory, and one sticks a vector potential into the proper form, that's a 4-vector potential, then the derivative of the vector potential, dA, is, in conventional developments, is some gauge term plus a field. So the 4 differential of the vector potential is the electromagnetic field in electromagnetism. And those things, those electromagnetic fields, the derivative of a vector by a vector, are bivectors and a scalar. So the transformation of a vector derivative, like the one defined on the previous slide, over a vector produces 2 kinds of components. One of them are field components, in the case of the vector potential. The other one are scalar components, which express the gauge. Now, the gauge condition for standard electromagnetism is that the 4 derivative, scalar part of the 4 derivative A is precisely 0. That's the definition of the Lorentz gauge. So that leads to a set of solutions. There are other gauges where that's non-zero, where, for example, the 3 differential is equal to 0. The Coulomb gauge is the gauge one uses for solving the charge of an electron, looking at charges. So there are different gauges. All of them are subsets of the Maxwell equations with different boundary conditions and with a different gauge, which allows one to find solutions. So we'll come back to that later. I just want to concentrate on what these things are at the moment and what they are in reality. We have a 4 vector, the alpha I. There are 3 vector part, alpha I. Roman letters here have 3 components, x, y, z, 1, 2, 3, for example. Greek letters have 4 components, 0, 1, 2, 3, for example. So alpha I is shorthand for writing alpha 1, alpha 2, and alpha 3. And an example of this is, for example, a 3 current density. Alpha ij has 2 components. It's a bivector. And an example of this is a physical quantity in this direction is the magnetic field. So if one starts with a 3 vector potential, as a 3 vector, does the derivative of this with respect to space, then that's the curl of A, one has B. If one does the time derivative, then one has E. So if you start with a vector A, x, y, z, derived by time, you get psi 0 x, psi 0 y, psi 0 z. And these things are the electric field. One starts with a vector potential. They're in the direction of alpha 0 I, the next one. One then takes that. So if one takes, another example of this is velocity, dx by dt. That's also in the direction of alpha 0 I. So if one has a velocity, if one has something flowing in x, and one multiplies that by y, one has something which looks like an angular momentum, something which is rotating in the xy plane, and that has some momentum associated with it. That's an angular momentum. So the direction, the nature of a quantum spin, an angular momentum, is alpha 0 ij. These are volumes in the 4-dimensional algebra that we've of space and time that we're developing. Complexity is arising very rapidly from the initial simplicity through this multiplication thing that we've defined. And of course, one can define a volume, alpha 1, 2, 3, x, y, z, and one can define a 4-dimensional volume. Now, this particular name that's on this slide, Quedgehog, is due to one of the people listening at the moment, and it's thank you, who was the first chap to come up with this name and write it on my board at Glasgow University a few years ago. So this is what we call the Quedgehog. Why do we call it the Quedgehog? Well, because we call alpha 1, 2, 3 the hedgehog. Why do we call that the hedgehog? Because it's a directed volume element. So it's like a volume element that can be either outward directed, like a hedgehog with the spines facing outwards, or you can also, in principle, have it inward directed. That would be like a hedgehog with the spines facing inwards, a very uncomfortable hedgehog. So we call that the hedgehog because of its nature, because it's either outward or inward directed. And the Quedgehog is the 4-dimensional hedgehog, so, or the quantum hedgehog, if you like. So, but although quantum hasn't been introduced yet, this is just talking about space and time. So we have a 4-dimensional basis with 16 linearly independent elements, unit elements, because they all square to plus or minus alpha p, in fact, to the unit element. They all square to unity. There are 16 of them. This is really a 17-component thing because it also has magnitudes. The magnitudes can take any real positive real number value. So there's a space there, which is a 17th space in this. So it sounds dreadfully complicated, but look, it might sound dreadfully complicated, but this is the space you live in, and you're all used to areas, carpets, volumes, size of a room. These are not weird, crazy things that you've never seen before. Some of them are a bit crazy. Like, who's seen time? Well, nobody. You don't see time like that. And anything that has time involved with it here is harder for we highly evolved monkeys to imagine with our 3-dimensional thinking brains. Wait a minute. Let's have a look at the structure of this 16-dimensional algebra. Does it really look 16-dimensional? Well, no, it doesn't. It really looks 3-dimensional. Now, what the hell is that about? I mean, 16 components. What do you mean 3-dimensional? Well, let's look at the structure of this. There are objects in here that come by themselves, and there are objects that come in threes, like one has, for example, time, one object, x, y, z, 3 objects. And you can slice and dice and move these in different ways. And Innes has been looking at other ways of slicing and dicing these things and putting them into different groups that are very interesting. But nonetheless, they come in 1s and 3s. So what are these threes physically, if we're talking about electromagnetism? If we're talking about an electromagnetism, which we will be very shortly. Next slide. Then, well, let's not talk about electromagnetism. Let's just talk about abstract things. We have a 3 of x, y, z. Now that's a 3-component system. We have one of time, which is kind of separate. So there is a 3-dimensionality of x, y, z, which is a 3-dimensionality that one sees, or one imagines one sees in a table. So the table which this computer is resting on, for example, looks pretty 3-dimensional to me. I can walk around it in 3 dimensions. I can't walk around it in 4 dimensions. I can't walk around the time of it. I can walk around the space of it. But what am I walking around the space of this table? What's the table really made of? Is it made of X, Y, Z? No, it's not. Because when I touch it, what I'm feeling is the electric, pretty much, interaction between my fingers and the table. It's a 3-dimensionality of field, of electric field that I'm feeling. And because this table has metal bits in it, it's got some magnetic field there too, and that's 3-dimensional too. And the electric field always was 3-dimensional. It's not a vector. It doesn't have 4 components, which you require for a vector in 4-dimensional space-time. It's always had 3 components. In any of the standard textbooks, there are 3 components of electric field and 3 of magnetic field, and hence 6 components of the electromagnetic field. We're not talking about a 4-dimensional thing here. We're talking about a 6-component thing. People sometimes call this a 6-vector. Which I think just confuses the issue further, but some people say it's an antisymmetric tensor, which is a better way of looking at this, and it's the way the advanced textbooks treat, or more advanced textbooks, medium advanced textbooks treat it. So, but anyway, so we've got a sort of 3-dimensional table here, which is a 3-dimensional electric table, because it has 3 components, and I've got a 3-dimensional magnetic table. Well, although I don't feel the magnetic stuff here, but it's possible to measure it. Possible to experiment on it. But there's also another thing here that's really quite important for this table, and that is that each of the little elements of this table are quantum particles that are spinning, and they have intrinsic spins, fermions, most of them, which means that they have an angular momentum of half h bar. And but how many components of that are there? Well, there are 3. There's spin in the xy plane, in the yz plane, and the zx plane. Spin in, so x, y, and z components of the angular momentum. And that's a separate table. So when I look at this table, I'm not looking at one table, I'm looking at 4 3-dimensional tables superimposed, an xyz table, a magnetic table, an electric table, and a spin table. And it's that table, or that set of 4 tables, which I walk around. If one takes on board this algebra that I'm making up might look as I'm making up as I go along here. So, right. Okay, so that's what I'm talking about here, is developing a quantum mechanics not in a spinor space, not in a complex space, but in a space formed of space and time and their products and quotients. X, Y, Z, T over a multiplication or a division, or both. So, okay, so what does this maths mean? If I go d mu psi g equals 0, what the maths means, more important than the maths per se, than the mathematical framework I'm just going to show, is such things as the space-time in which it's embedded, properties of that space-time, the relativistic properties of that space-time, for example, embodied here by putting in absolute relativity. The most important thing for a stable solution, for something that describes a particle that endures, is that it has coherence. Now, this is where the quantum mechanics comes into the thing. Something that coheres, coherence means 2 things. One is that it sticks together, so it remains the same thing, but it also means something that remains in phase with itself. So if we have an object, a quantum object, an electron, it's going in some sense round and round in circles, the solutions of the Dirac equation, very rapid oscillations, Zitterbewegung oscillations at about 10 to 20 plus hertz. It's oscillating in 3 dimensions. This is your quantum wave, if it's waving, but it's waving in place, so it's as a rotation rather than a simple wave, is that it coheres, it's coherent with itself. That implies a kind of symmetry. That symmetry is a symmetry that the thing has to be, well, rotationally invariant is what we'd say. It has to be spherically symmetric eventually, or at least rotationally symmetric, like a. These are dynamical constraints on the system. D mu psi g equals 0, as I said before, is implying that the change is no change, that if I look at the electron a quarter of a phase later, it'll look like the same electron, it'll be identical. So although everything may have changed within the electron, one bit's changed another bit, that the electron as a whole remains, it coheres. So this is an equation expressing coherence. So the system before and after the operation of the four-vector derivative is the same. So each element within that doesn't preclude elements within themselves. In fact, if you hit anything with a four-vector differential, it's going to change its form. If you derive x by t, the answer is not going to be x or t, it's going to be something in the direction of velocity. The x by dt is a velocity. So it's going to, this equation expresses a possibility of transformation between forms. But what you must have, if you've got a coherent system, is something else that's transformed to your things that were your x, y, z, t before. They fill the gap. So things must replenish one another in a self-sustaining flow for a stable solution such that the flow is stable, obviously. And that's more important than the maths. The thinking about what has to happen here and finding a solution is more important than the mathematical framework. So, what's different about the Maxwell, between this equation and the Dirac equation, I'm going to come to very clearly shortly, but the main differences are, first, this one doesn't have an extra space, the square root of -1, which is not a physical space, but a mathematical space. It doesn't need it. And it doesn't need it because the properties of the elements within the more complex, hypercomplex, you could call it, Clifford space, have the properties of squaring to -1 and +1, some of them. So all of the machinery you need in there to do waves is already there without putting in a scalar square root of -1. And we're going to get wave functions that look more complicated than the wave function we put up for the Schrodinger equation, and they are more complicated, but at least they're based on something which is real. Lines, planes, volumes, hypervolumes, etc. So also that psi g is operating on such, what does it contain? Well, it contains things like spin and current and field. It contains things that measures real things rather than an abstract spinor or a complex exponential, which does not exist in any in reality, or at least in the reality that we're of x, y, z, t, and root energy. So there are mass terms in this equation, d mu psi g equals 0, because, as I've said, psi p and psi q, the scalar element of its dual, transform like rest masses. But they're also subject to the same dynamics as the fields and the currents and everything else. It's not just putting a lump of mass into this, it just sort of sits there and does mass stuff. It's part of the dynamics. It's different in that respect. So the resultant new solutions, and there are solutions to these equations, over and above light, is going to emerge as half-integral spin fermions, physical spinners, rather than being put in just in mathematics to have the properties which they're required in order to get solutions for the maths. So let's have a look at that. Here we are. So here is what you get if you do this. So this, again, if you want more details on this, it's in the recent paper. And this is thinking about, this is a theory which allows one to think inside what's happening in elementary particles. Now, why is such a theory important? Why is such a thing important? Well, because we don't have it. the theories which I talked about in the last lecture, all of them take certain things as a starting point. They take the particles which form the world we live in and as given and start from there. Now, they're very, very good theories, and they have immense utility starting from that starting point of those of electrons and photons and protons and neutrons and the stuff which we are and everything that we observe in the universe is made of. But they don't say what the electron is, why it is, and how it is. Now, let me come out from the slide for a little bit and just talk about physics and talk about experiment. I'll talk about a journeyman experiment that I was doing at CERN back in 1980. Super Proton Synchrotron had just come online, and we just had a huge order of magnitude increase in how closely we look at the inner nature of matter. So we had 200 GeV muons coming thundering down from the beamline, and we smashed them into a hydrogen target, liquid hydrogen target, and had a look at what happened. So we're using these electrons as a probe of the nucleon structure, what's happening inside protons and neutrons. Actually, protons. So it was a proton, it's a hydrogen target. So let's imagine that kind of, I said that one has to think in terms of nature. Let's do some, forget the maths, let's do some thinking. So imagine what this is like from the point of view of either the hydrogen sitting there being smashed by muons. Income is a 200 GeV muon. Now, the mass of a proton is roughly a GeV. GeV is expressed in energy terms. So it's roughly a GeV over c squared, if you want the units. So these things have got 200 times, although the muon's roughly 10 times lighter than a proton, the incoming stuff is coming in at 200 times the massive energy of a proton. These are incredibly energetic particles coming in, they hit the proton, smash, all sorts of stuff comes out. So that's from the point of view of the proton, and one's probing the proton with a lepton, an elementary lepton, the muon, in order to get a fix on what's happening to the proton. And that proton's held together by the strong interaction, but the strong interaction is weak compared to the amount of energy coming in. It just blows up, produces particles, more protons, antiprotons, electron-positron pairs, photons, sigma particles, all sorts of exotic matter, J psi's, pi zeros, all sorts of stuff comes whizzing out of this. More comes out than in a sense goes in. But as Viv said in one of the preambles just here, after a little while, all that stuff decays back, and one's left with just the initial particles one started with, which one's left with electrons and protons, and pretty much such a system. One starts with neutrons, kind of can be in there in matter too, but this thing's been hit so hard that matter, I'm not really talking about matter, you're talking about new elementary particles. But I want to look at this from the point of view of how the muon would feel about this, just to expose something that's missing in science as it stands. Imagine you're in the frame of reference of the muon. So you're sitting there with the muon and its friends in the muon beam. What the muon sees, it doesn't see itself smashing into the hydrogen. What it sees this hydrogen rushing very quickly towards it and smashing into it. So let's imagine ourselves just being the muon. So, and muon name is pretty good in the sense that if we just replace the A with a diphthong uo, or we can go from human to hu muon. Imagine you're a hu muon, and you're sitting there as a muon, waiting for the possibility of some proton smashing into you at some immense energy. What does it look like from the point of view of the muon? Well, muons live for roughly in the lab at roughly 10 to the minus 6 seconds. But muons also have an oscillation frequency that's about 10 to the 21 hertz. So a muon tends to go through, will in its lifetime go through 10 to the 14 odd cycles. How does that compare to the number of cycles that a typical human goes through? Well, the rate our brains work is roughly 1/10 of a hertz, and we live for 70 years. So a human will go through something like 2×10 to the 10 seconds in a lifetime. In the muon lifetime, it will go through far more than that. It'll go through 3 million years, 3 million muon years of cycles. So if the muons were intelligent as a human, they'd have plenty of time to develop civilization and habit. shortly smashed to bits by a thundering proton. Anyway, here we go. So imagine this proton coming in. How big is that proton coming in, and what's it made of? Well, with the relativistic corrections, it's coming in at 20,000 times the mass energy of the muon. So that this will be like something of 2 million ton, a 2 million ton ship coming at you at the speed of light in human terms, and it's going to hit you. So that's pretty serious stuff. But these muons are really, really hard. They're so hard that when that happens, and this is something coming at you, it's a ship held together by the strong interaction, by the strongest interaction known to humans. But what happens when the inevitable happens and this proton hits you is the muon is completely unscathed by that interaction. It just bounces. And it's the proton that shatters. It's the strong interaction that's disrupted. Whatever the muon is, whatever's cohering the muon, whatever's holding it together, is a far stronger thing than the strong interaction. We need to understand as humans how that works. Not that elementary particles exist, they do, but why and how and what they are. And that knowledge is still not there in the standard model. Now, we've looked at an element of the standard model, how to build quantum mechanics, looked at relativistic quantum mechanics, which is in the standard model, said, maybe it's a bit iffy here and there with a square root minus 1 and a lump of mass. Where does that come from? How is it associated with the four-dimensional derivative of the momentum, energy momentum that's sitting in there in the Dirac equation? Well, it's just stuck in there by hand. So maybe it's not the ultimate theory. And look, the standard model gives away a clue of what it is really just by its name. It's called standard model. We're talking about a model. That's a very sophisticated model. And it has elements that are theories. It has relativistic quantum mechanics, quantum electrodynamics, quantum chromodynamics, Newton's laws. They're all in there. Maxwell's equations, all in there. But they're all in there as separate parts that sort of have gaps between them. We want to move to something which can describe why and how muon, or ultimately electron, which is what it's going to decay to, that's even harder than the muon. So those things never, as far as we know, are destroyed by any process, with the possible exception of when you start getting to really astonishing things in black holes or neutron stars or stuff where they start fusing with protons to form neutrons, or at least if what comes out of a neutron decay, which is an electron, a proton, a neutrino, so something's happening there, neutrinos getting into it somehow, is a proper picture of what happens there, which it may not be. But let's go to experiment. Back to the slide. Experimentally, you can produce electrons and positrons, and you do so in huge numbers in an electromagnetic shower. In my old lead glass detector, for example, at CERN, come in with an energetic electron or an energetic photon. The thing spalls into photons, will generate electron-positron pairs, which will generate photons, which will generate electron-positron pairs, and the whole thing blows up. If you're at high enough energy, there's thousands of these things being created all over the place. And the question that really interested me all those years ago when I joined CERN is, how does that sort of thing work? How does matter transform to light and light to matter? And what's up on the screen in front of you at the moment is a picture of that happening, of two photons going to a Williamson van der Mark pair of electron and positron. So how does that work? Well, we developed that theory, that quantum mechanics, which just came out, that d mu psi g is equal to 0. Now, why do I think that might have any value? Or how can I convince you that might have some value? Well, if you just take out of those 16 components, the 6 components, which you know are the electromagnetic field, the bivector components, top right of the slide up here, and you do that 4 differential, that 4 vector differential with absolute relativity built in on just the field part, set that equal to 0, and then, as they say, do the mathematics, and work out what that means in terms of electric and magnetic field, you get these 4 equations. Those 4 equations are just the Maxwell equations. That element of the theory is identical to classical electromagnetism. It doesn't contain charge yet, but it's got all of the stuffs of all of the mechanics of the Maxwell's equations. Now, if you take the full equation, so now we put the other 10 components back in, and we do that on the full thing, and you just do the maths once again, then all of the derivatives of that, written in familiar language with the D0 and grad operator, the nodal operator in there, looks like this set of equations. There are not 4, but there are 8 equations. There are some unfamiliar terms. If you get rid of the terms, the 16 one at a time, so any given equation, this first one is saying that the divergence of E plus the time rate of change of the pivot of the scalar component is equal to 0 in this case. What that means, it means the divergence of E need not be 0 in such a thing, provided you have a rate of change of mass. You have a matter exchange. And that matter exchange could constitute a charge in this new theory. Now, what does that sound like, and what is that related to? Well, in Maxwell's equations, what you do to make Maxwell's equations into the full set of Maxwell's equations is you put in the charge by hand on the right-hand side of the divergence of E equation. Say it's equal to rho 0 over epsilon naught, for example. This equation is telling you that an equivalent to that is an exchange of mass. Now, in quantum electrodynamics, the charge is not put in as a field, but it's put in as the probability that mass exchange will happen. And here's a theory that says the same. It says that mass exchange can constitute something, can constitute a non-zero electric field divergence if that possibility exists. If the possibility doesn't exist, there's no mass, then divergence of E is 0. But if there is some mass and it's in the right kind of distribution, there could be a possibility, and that changes, that gets exchanged, that changes with time, and that could constitute a charge. That's what that equation is telling you. Similar thing for the quadravector here, the 4-dimensional thing here, but that could be 0, of course, that term, and then divergence of B would be identically 0, which is probably the case. And there's some extra terms as well in the equivalent of the Maxwell's equations up here, which have the gradient of P and the gradient of Q, as well as the curl of B and the time derivative of E, for example. So the equations are more general. They reduce to the Maxwell's equations in the simple limit where you just look at the field, but they have extra terms in the dynamical mass, not a mass put in by hand, but a mass which is a dynamical part of these equations, essentially. So here's the Dirac equation again. Compare this equation, d mu psi g equals 0, where the masses are dynamical, the Dirac equation, where the masses are put in by hand. But otherwise, if you take that bit out, if you just ignore the R, which you shouldn't do, but and you ignore the M, then these are the same equations. So they're similar equations. They're both linear equations. They both have a similar underlying mathematics, the mathematics of relativistic Dirac algebras. They're one slightly more complex than this one, and it's also slightly more complicated in that there are more terms. And it's also very beautiful, but slightly less beautiful than that one, in my view, at least for me. So that's the theory. That's a new theory. It's not the ultimate theory, I don't think, but it's a new linear theory that it contains both light, as in Maxwell's equations, but also starts to put matter into the loop just here. So how does that, let's have a look at that working. What the solutions look like in this. Solutions to Maxwell's equations are the solutions to Maxwell's equations. We know what they look like. And indeed, one has the same sorts of solutions here. But let's try and construct, not quantum mechanics, which is what we did before, but a solution to quantum mechanics. How do you write down a solution in this new paradigm? You don't come in with a complex exponential wave function. Why? Because you don't have the square root of -1, so you can't. And you also have to impose the rule of absolute relativity, that no quantity can appear without its proper vector. So you do that. So here is a trial wave function. Doesn't work, but it's a trial wave function. Here's an exponential. Oh, this one does work. I've got Yeah, but let's do it without this bit here. We do alpha 3, that's the unit vector in the z direction, times z, kz. That's like alpha 3 squares to negative unity, so like square root of -1, that's fine. That's a wave, as opposed to a falling or rising exponential. But without the alpha 0, 1, 2, the other component, alpha 0 squares to plus unity, that thing looks like a falling exponential. It doesn't describe a wave. You can transform it to a wave by introducing a unit angular momentum. And if you multiply this thing by unit angular momentum, then that thing times alpha 3 and this thing times alpha 0 both give things elements which square to -1 and hence describe a wave. So one could argue this might be a possibility for an element of an electron wave function. If one expands that wave function, it has not one phase but two, and it has not a couple of components in the imaginary, it has four. And what the four components are of this particular wave function is they are a mass, an invariant mass, an invariant dual mass, and an electric field and a magnetic field. So four-component wave function with electric and magnetic field and mass. And that might begin to sound a bit like an electron, but I think it's more complex than this simple wave function here. However, this is a very interesting wave function because, why is this so interesting? Because if I multiply it by the fields of a physical photon, that is an equal and perpendicular electric and magnetic field, then it transforms from a four-component wave function to a two-component wave function, and the mass terms all cancel. And you end up with a massless, that's this thing, wave function that has some very special properties. And those special properties are that it transforms like a photon. Now, why is that special? It's special because, not because it's new, apart from anything else, to have something which transforms naturally from to any energy in one direction and to seamlessly to zero energy in the other direction, just on setting a Lorentz transformation loose on it. It's a relativistic function, and it describes E as h nu for photons as the energy change, as the frequency changes by changing the Lorentz frame, so too does the, as the frequency increases, so too does the energy if one does this properly relativistically, linearly. So it obeys E as h nu. And it transforms space and time in exactly the same way that they transform in reality. And that's going to be the subject of a later talk to show that, but take my word for it for the time being. Or wait for the future talk, of course. This wave function allows one, this is a photon wave function, this is describing what's happening here. This is an element of an electron wave function that has mass as well as electric and magnetic fields. If you go to the next level of this, which I'm again going to do in a later talk, and look at forces or at momentum flow in such systems, in the presence of mass, what does mass do for you when you put it in here, as opposed to massless systems or rest massless systems like the photon? What it does, it deflects. There's an interaction in this thing between the mass and the electric field, the rest mass, the P component and the E component. One looks at the generalization of the four momentum interact with each other in such a way that the pointing vector, which is E cross B, gains a component perpendicular to E cross B. It's a component. It's the pivot times the electric field, which is perpendicular by definition to E cross B. What it means is that instead of the momentum going straight on, it curves. And that curving momentum is the beginning of something going round into a loop. Now, coming back from the equations to the more overarching principles, if something is going to be coherent, it needs to cohere, it needs to come back on itself. And there's a general theorem due to Gordon-Pask that topologically, any such thing that goes round and round in circles is really topologically a torus. Talking about something that goes somewhere, goes around, might do some complicated things in between. The torus might be rotating, but internally, one has a system that comes back on itself, and it comes back on itself in a smooth way. So we're talking about something which is round. Then topologically, that sort of thing is a torus, and that's what's drawn here. It's a double loop around a torus, but it's not just drawn here. It's actually constructed mechanically. What do I mean that it's constructed mechanically? So how do you make an electron out of an electron-positron pair out of a pair of photons? Well, I'm going to use a belt to illustrate that. Photon is something that goes around in a single wavelength. So here's a single wavelength model of a photon. The electric field is outward directed from this belt. The magnetic field is in the plane of the belt. What I'm going to do is I'm going to make that thing go round and round in circles. So I'm going to bring one complete turn here, 4 quarter turns in the belt. I'm going to bring that round and join it up. And if the thing has any, here it is. This is just a mechanical model of that thing.
John, I don't know that we can see what you're doing actually on the video. You'd have to stop sharing screens.
I have to stop sharing. Oh, good man. Okay. Right. I'm going to come back to stop sharing. Thanks for that interruption, Arnie. That's good. Can you see me now?
John, I don't think you need to worry so much about that. I can insert your iPhone recorded video on top of this and expand it. So the inlay expands and then you show it. So go on.
Good man, Joachim. Well, okay, I'll do that, but I'll get it up on screen just now. I've stopped presenting, so you should be able to see me. Is that right? And Arnie, will the video also show this?
Yes.
It will. Okay, let's keep it on this, and I'll show you what's happening again. So just to recap, so and good man, Joachim, we'll put that in later. I've got a belt here, and I'm putting a twist onto the belt. Let me just see how well that shows up. So what I've done is I've put a full twist onto the belt that represents the twisting incoming, that represents the field distribution of a photon. How can that twist up? Well, it can't twist up and by itself. It needs a partner photon in a spin zero state, and it needs to lead to a charge zero state at the end. So it's not going to produce an electron by itself, but it could produce an electron-positron pair, which conserve all the required things from the overarching set of constraints, which I talked about last time. Here we are. What I'm going to do is look at what one element of that looks like. So if we look at one element of that, bringing these two things together and attaching them, one ends up with something that looks like this. It's a belt. And the twist is still in the belt, but if there's some torsion here introduced by an energy minimization of whatever form, in this case, it's really the twist on the belt that's providing the tension. But in an electron, what it is, it's the cancellation of fields, because if you've got a self-recreating system, it's going to try to reach a minimum energy. And that minimum energy has to be such a deep minimum energy that the strong interaction looks like a pushover. It needs to be strong compared to the strong interaction by a lot. Now, I'm going to come on to how and why that works later. But for the time being, just imagine that it happens. There's some mechanism for making this twist happen. Kind of something like this. It's that double loop, which is on the video behind me. It's still visible there. It's the Williamson van der Mark electron that we invented back in 1991. And this thing has the property that if you look at the electric field on this, electric field was outward directed from the surface of the belt. It's everywhere outward, and that object is charged. And that's how and why, in this theory, you can create an electron from a positron pair, from a pair of photons. You can trap light inside matter. That's how it works within this, informing solutions to this new theory. Now, if you go back to the theory now and see where that comes from in the theory, and you look at the momentum, you can see the momentum turning, and the momentum has to turn in the direction of the electric field. So if we imagine now this is an electron, it has a radial electric field coming out effectively, or going in the case of electron, it's an inward directed field, a hedgehog field going in, electric field. Then you see why the thing is looping. It's looping because as it moves photon-like around the belt, it has a component in the direction of motion, but it has also a component of motion perpendicular to the self-generated electric field, which bends it. And provided those terms are the same magnitude, one will get a double loop. They have to be the same magnitude, which means that whatever's forming this has to have the same amount of stuff in the mass as it has in the field. And that's exactly, of course, what those wave functions that I just put up do. They have an equal division between two mass terms and two field terms. So that's the kind of new solution you get from this new theory. It's a quantum mechanics. What does quantum mean? It just means countable, comes one at a time. How does the thing get quantized? It gets quantized because it must be coherent. And it's that coherence condition that it goes around, it's just that it goes round and round in circles, guys. But it self-recreates itself. It's an integral entity. That's the quantization. So although it contains classical electromagnetism in 6 of the terms, it also acts as a quantum mechanics, as you might expect, because it looks so like the Dirac relativistic quantum mechanics in that it has mass, and it has mass terms as well as momentum terms, as well as full momentum terms. So it's like the Dirac equation. It's the same order as the Dirac equation. It has the same number of solutions as the Dirac equation. It has spinor solutions like the Dirac equation, because this thing is a physical spinor. It goes round twice in space before you get back to where you finished. It has a 720-degree rotation. You can calculate the charge from this thing, and it's close to the electron charge. See Martin and my 1997 paper. It has exactly half-integral spin, which you can calculate from the momentum of this and its size. It turns out to be exactly half-integral, like the electron, half-integral spin. It's a fermion in that, first of all, it has half-integral spin. So from the spin statistics theorem, it's a fermion. But also because the thing is double looping intrinsically. We're talking about something which is a physical spinor. So it's a fermion in all sorts of ways. It's also a fermion in that if you try and put another one of these things on top of each other, and there's a paper I'll put up as well, I gave in Mendel in 2012, I think, 2012, that's right, where I was claiming that the uncertainty principle arises from this. Put two objects on top of one another, you get 4 times the energy. Put them spin anti-parallel to each other, and you get just twice the energy, which conserves energy. So and what that means is the exclusion principle is, compared to the strong interaction, a much stronger force. If you just do the run the magnitudes. So anyway, in conclusion, this new theory is an analytic theory. It just contains its differential equations. It encompasses Maxwell's equations. It extends relativistic, or it is a relativistic quantum mechanics. So different to the Dirac equation, but similar order. It explains what the electron is inside. What the electron is an electromass magnetic system, something that contains elements of rest mass, an electric and magnetic field, and matter. And explains how they work and how the dynamics internally works as well, because the electron doesn't just contain field of matter, it also contains spin and current, an internal current. Those spins and internal currents, they're not separate things from the mass and charge, because they are generating and generated by each other. So this may not be the equation describing them. D psi equals 0 may not be what's describing the electron. It might be D2 psi is equal to 0, that's a wave equation, is what describes it. And that may very well be the case, that you only really come back to the same thing after half a turn, after going once around the loop here. That may be the case. This is not necessarily also the equation describing the universe or the operation of the universe. It could be D2, it could be D4. Certainly at the stage of D4, of 4 differentials, you get back to where you started from. So and that really must be in a self-sustaining system exactly the same as the system you started from. You back to where you started from. So certainly D4 of this thing is equal to 0. It's going to be a valid solution. Whether D of this thing by itself, that's not necessarily the case. But the development of these mathematics is, at least one can think about what's happening within the electron in terms of fields, in terms of lines and planes and volumes, and hypervolume in terms of spin, in terms of field, in terms of current, in terms of mass, in terms of things that we deal with all the time. If you ride a bicycle, that's why Quicycle project is the quantum bicycle project, a short for. If you ride a bicycle, all of those things are happening. Angular momentum, mass, speed, all of those things are playing a role there. And quantum bicycle was originally envisaged as what would happen if you took bicycle into space and started pedaling. And this bicycle had wheels and 3 perpendicular planes. What would happen? And that has analogies with it's not the same as the motion of the quantum bicycle, of the 4-dimensional bicycle, and hence the term. Right, now I could start sharing again, I think. I'll do that and then conclude, and that's it. Okay, there we are, we're back on this thing. So down at the bottom of this slide, in my view, this theory is a better description. It's Dirac as it should have been.
John, you're not sharing.
I'm not sharing it. Just a moment, I'll come back. Yeah, I've done that before, haven't I? Right, I need to click on this and hit share. Right, okay, good. Thanks, Annie. Right, so now I should be sharing, and now you should see the presentation. Okay. Okay, so now down at the bottom of this thing, in my view, this is Dirac as it should have been. It's a dynamical, linear, relativistic quantum mechanics theory. Let's see what the next slide is. Conclusions. So pretty much what I just said. Base this thing on space-time and square root energy, but introduce some mathematics and mathematics of reality. It covers a surprising amount by itself of current physics, especially encompassing such things as the Maxwell's equations. It also, so it extends Maxwell, it generalizes the Dirac equation to putting mass in a dynamical way, in a way which is consistent with the fields. So in Dirac, if you want to look at the fields, you put them in through the vector potential, sort of add stuff on top. Here, those come in naturally from the beginning, in the same way that they're brought into the Maxwell equations. So I think it's better, but I would think that, wouldn't I, of course. It also brings up things that underpin quantum electrodynamics. So underpinning, what do I mean by this? I mean that we're talking about the relationship between mass exchange and field, how that fits in between theories like quantum electrodynamics, a beautiful theory which calculates stuff to 10 decimal places, how that fits in with the classical electromagnetism 150-year-old theory of Maxwell. So it underpins QED, it gives the starting points of QED because it generates the charges and it explains the photons on which quantum electrodynamics is based. Quantum electrodynamics is at root a theory of the exchange of photons between charged particles. And this underpins QED in that sense. It introduces new kinds of wave functions based on the principle of absolute relativity that are fully relativistic, and deals with proper field superposition, which is going to be in a later talk as well, that shows how relativity works to give linearity both to energy and to energy density in such solutions, both to root energy and to energy density in such solutions. That's what I should say. So as soon as you put a root mass term in, you get new solutions. Those new solutions are charged, localized, half-integral spin solutions. They're physical spinners, which the obvious identification with these things is the electron and positron. And the elementary particle, that something is an elementary particle, is defined by topology and symmetry, not size, how big it is or how light it is, or a washing list of so-called quantized properties. If you have a bunch of quantized properties belonging to an electron, what those quantized properties are there a list of the things that you don't understand about it, think about it, lepton number, spin, charge, G-2, all sorts of things that you don't, you give a name to it, but that's just naming things, it's not understanding them. Also, the theory explains how the electron can appear so very small in scattering. I didn't go into that in the talk, and yet so very large in the solid state. How does that work? Well, the charge you calculate in the electron model is size independent. See the 97 paper of Martin and myself. And that means that an electron can maintain its electronness at any size. The reason it looks small, and this is one of the insidious things about physics, people think the electron has to be a point, because at CERN, you do scattering experiments which show it to be point-like. Now, people who are not in the field don't understand the difference between point and point-like. Why do these people say point-like? Sounds like Geordie accent here. It's point-like. The like matters. The fact that it's point-like and not a point matters. What a point-like thing, as opposed to a point thing, is it something that acts like a point would act, in the sense that in scattering, it looks smaller always in a way that scales with the energy. So the harder you look at it, the smaller it looks. And that happens in a way which is size, which is energy independent. Now, that scaling is only an approximate thing. If you want to look at these, look at some of my papers on structure, and my colleagues' papers on structure function of the proton. There's a region of the momentum transfer where that is size independent. There are other regions where it varies, plus or minus with size, but it's an approximate symmetry, that point-like thing. And a point-like interaction is, for example, the interaction between the center of mass of the Earth and the center of mass of the Moon. They act like 2 point masses in terms of the way they rotate around one another gravitationally. But if you want to think that the fact that that happens means the Earth is a point or the Moon is a point, just look around you. It explains how the electron can appear so small in scattering, because if you scatter two of these things together, they shrink in relatively in the same way as a photon. And it also explains how they can be so very large in the solid state, because provided you have the same topology in the vacuum that's produced effectively in a background of positive and negative charges that's uniform, the whole thing simply expands because all of the energy scales are much lower, because everything can share. So it's only if the electron is out there in space that it needs to be really seriously dealing with only its own mass density. If you're in a pile of mass and a crystal of mass, it could be very, very, very much larger. It explains how the electron does that trick of scaling from very large to very small. But the main thing about the new paradigm is it just allows you to think about things that otherwise you couldn't think about at all. It's a language for the brain, a new one. That's the end of the talk. And I'm going to stop sharing and pass it over to the general discussion.
Okay, we'll stop the recording at this point for a break.
Good.